Hi everybody, welcome to another video in Course Algebra, section 6.4. On this section, we'll study about the inverse of a matrix and matrix equation. In order to define an inverse of the matrix, we have to define an identity matrix first. So a square matrix, by the way, the square matrix will have the same number of rows as the number of columns. So it have to be a square matrix. And in that case, for every square matrix of the same order, so we have the square matrix and another for every square matrix A of the same order, A times the identity matrix is equal to the identity matrix times A equal to the matrix A itself. So in that case, the matrix R is called the identity matrix of that order. So pretty much the role of the identity matrix is acting like number 1. So like in numbers, 1 times x is the same as x times 1 is equal to x. So the role of identity matrix is like number 1 in the real number system. Right. Except that we define multiplying in the real number system and multiply in matrix, and this is matrix multiplication. We define those multiplication differently. Alright. Example 1. Now, of course, that's the way we define it, but in application, the identity matrix is the matrix. First of all, this is a square matrix. So we could say 2 by 2 or 3 by 3, but because it's a square, so the numbers of rows equal to the number of columns. So we only need one number. So 2 rows, 2 columns, 3 rows, 3 columns. And what we see here is we have 1 on the diagonal, the main diagonal, the northeast, southwest diagonal. And 0 everywhere else. So in the identity matrix have to be a square matrix, and we have ones on the main diagonal. The main diagonal, or we call the northeast to southwest diagonal, and 0 everywhere is everywhere else. So it's everywhere else. That gives us the identity matrix. Right. Now we have the identity matrix which arc like number 1. We can define inverse of a matrix. By the way, inverse of the matrix is unique, so we can say the inverse of the matrix if we want to. Right. Let A be a square matrix. So again, on this section, we only talk about the square matrix. A be a square matrix. If there exists an n by n matrix, say A inverse, such that A times A inverse equal to identity matrix, and the inverse times the matrix is the identity matrix itself. So we will need both of them. A times A inverse and A inverse times A. If this is satisfied, then we have we say A inverse is the multiplicative inverse of A. Once again, the matrix is unique, so that's why it is the inverse. So now if we have the analog of the numbers, for example, if we have 2, then times 1/2 is equal to 1. But in number, we don't have to write it, which is that's good enough. We don't really need 1/2 times 2 equal to 1, right? But in matrix, we need to have both. Why is that? Let's just go back on the previous, the last example on the previous section. We have A times B. This case is the 2 by 2 matrix, and B times A is the 3 by 3 matrix. And obviously, we can see here, in general, A times B is not the same as B times A. So because they're not the same, so that's why we have to check to see that the product in either direction equal to the identity matrix. Right, let's go to this example. Show that B is the inverse of A if A is that and B is that. So simply we just check two things. First is A times B equal to I. So A is negative 1, 3, 2, and negative 5. That is A times B, 5, 3, 2, and 1. Right, we talk about multiplying matrices together on the previous section, row by column. Negative 1 times 5, 3 times 2, so negative 5 plus 6. Negative 1 times 3, 3 times 1, so minus 3 plus 3. Two times 3, negative 5 times 1, so that is 1. And then 10 minus 10, 0. So yes, so this one, check. That is the identity matrix. Now we take B times A. And is that equal to the identity matrix? 5, 3, 2, and 1. Negative 1, 3, 2, and negative 5. Right, row times column. That's negative 5 plus 6, so it's 1. 15 minus 15, 0. Negative 2 plus 2, 0. 6 minus 5 is 1. So this is once again the identity matrix. So we have B times A is equal to the identity matrix. So A times B equal to identity matrix, B times A equal to identity matrix. We have both direction of the product. So in that case, we say so A and B are inverse of each other. The inverse is unique, so we can just say A and B are inverse of each other, or we say B is the inverse of A, or A is the inverse of B. Right, we have a theorem. Now this theorem only works for 2 by 2 matrix. Now if the matrix A is A, B, C, and D in that order, then the inverse of A is equal to 1 over AD minus BC. And then when the matrix, we have D and A interchange, and negative B, negative C. So let's just, first we have AD minus BC, so that is kind of the cross product, if you will. And then we'll, for this 2 and 3, we swap places, so we interchange, D go there and A go there, and then B and C will change the sign. So change the places, change the signs. And then 1 over AD minus BC. By the way, 1 AD minus BC equal to not equal to 0. If AD minus BC equal to 0, then there will be no inverse. So A does not have inverse. Just like when we have number 0, this number 0 doesn't have the inverse because divided by 0 is undefined. So 0 doesn't have the inverse. Just like this, for some certain situation, we will not have the inverse of a 2 by 2 matrix. So once again, 1 over AD minus BC, and then the main diagonal we change the places, the other we change the signs. But the bad news is this only works for 2 by 2. If it's more than 2 by 2, we're just going to use a calculator, because do it by hand will take a lot of work. And we will not cover that in this class. Right, let's just take a look at first example. Find the inverse of the matrix A, 1, 2, 4, and 5. So the inverse of A equal to 1 over 1 times 5 minus 2 times 4. And then 1 and 5 interchange the place. 1 and 5 interchange the place, and 2 and 4 change the sign. Right, so we have 1 over 5 minus 8, so 1 over negative 3. And then we just have 5, negative 2, negative 4, and 1. Now multiply negative 1/3 into it. We have negative 5 over 3, negative 2 over negative 3, so 2 over 3, 4 over 3, and negative 1 over 3. Right, by the way, if we want to do this by hand, we can just, if you want to store the matrix, we do that, or we just enter in the home screen alpha zoom 2 by 2, 1, 2, 4, 5, and the inverse is this button, right? And then we can change to fraction, right? So simple enough. Of course, when we have 3 by 3, we have to use the calculator. Of course, that's one way to do that. Another way is to store into the matrix. So go to edit, 2 by 2, then 1, 2, 4, 5, and then we say second matrix again. You see the matrix A is there. Hit enter and just hit that button. Of course, we have the same thing. Right, so that's the first part of matrix equation. For 2 by 2, we can do that. If we have 0 at the denominator here, we just say the matrix has no inverse, because that could be undefined. Right, second part of the section is matrix equation. So matrix equation, we use matrix equation to solve system of linear equation. Consider the equation. Now, we have x plus 2y equal to 3 for x plus 5y equal to 6. Now, if we look at the numbers on the coefficient of x and y, we have 1, 2, 4, and 5, right? So, sorry, 4 and 5. So, the matrix A is the matrix of all the coefficient of x and y. The matrix X is the matrix of variable x and y. And then B is just the other, on the other side of the equation. Right, so in that case, we have AX equal to B, the matrix equation. So how do we have that? So it's very simple. If we have the matrix, say 1, 2, 4, and 5, that matrix A now times the matrix X. So 2 by 2 times 2 row 1 column 2 by 1. We will have a 2 by 1 because the middle number match. So this entry, first row, first column, so 1 times x plus 2 times y. And this entry, row times column for x plus 5y, which is x plus 2y for x plus 5y. Of course, that equal to 3 and 6 on the other side. So pretty much we just write all the coefficient together as the square matrix, and then all the variables as the column. Right. And then so we have ax equal to b. So this is called the matrix equation. From this matrix equation, if we want to solve for b, if it is number, we divide by a on both sides. The only problem here is in matrix there is no division, but we do have the inverse, and that's what come into place. If we multiply the inverse on both sides, inverse matrix times the matrix itself is going to be identity matrix. Identity matrix times x is going to be just x. So that's why we can say x is equal to A inverse times B. So this is the solution to the matrix equation. So we have this theorem: if A times x equal to B, then x is equal to A inverse B, provided A inverse exists. If A inverse does not exist, there's no solution. Right. Now let's look at this example. Solve the following system of equation. So we have this, and so we just said we have the matrix A, coefficient 6, 5, 5, and 4, and then the column for variable equal to the other side. And for this, we say this is A, x, and B. So matrix equation A times x equal to B. So x equal to A inverse times B. Inverse of a 2 by 2. Suddenly we have the formula for that. So 6, 5, 5, and 4. We're going to find the inverse for that. Times B, 13 and 10. Right. And find inverse of a 2 by 2 matrix. Multiply 6 times 4 minus 5 times 5. And then 6 and 4 interchange their places. 5 and 5 change the size. So multiply 13 and 10. Right. So 24 minus 25, so just minus 1. 4, negative 5, negative 5 and 6. 13 and 10. Just negative 1 times all of this, so I just change the sign of everything inside. Negative 4, 5, 5, negative 6 times 13 and 10. Right, rows times column. Negative 4 times 13 is negative 52 plus 50, so that's negative 2. 5 times 13 is 65 minus 60. Right. Of course, we can always say it, we have the matrix A, 6, 5, 5, 4, inverse times this matrix will have 2 rows but only 1 column. 13 and 10. So indeed we have negative 2 and 5. So once again we have matrix equation. The corresponding solution is that. Right, next we have the system of 2 equations. So we will have 3 by 3 matrix for the coefficient. Right, coefficient for x, y, and z from 3 equations. 2, 6, and 6, 2, 7, and 6, 2, 7, and 7. The coefficient matrix, so that is A. Next, variable stacked in a column, vector into a column, and then another column on the other side. Right, so here we have A times x equal to B. So A times X equal to B. So X equal to A inverse B. Alright. So here, remember, for 3 by 3 matrix, we will not find the inverse by hand. We just use the calculator. On the test, it might be given. In that case, we just take the inverse times the matrix B. Right. This time I just want to store into the matrix B. If there's something in there already, we just can always just override it. 2, 6, 6, 2, 7, 6, 2, 7, 7. Alright. So we have the matrix A and inverse. So that is the inverse if we want to find that. But since we just have A inverse times matrix B, of course I forgot to store matrix B, but that's alright. I can always just say it. Enter everything on the home screen. I can just do that. I should just write this down. So we have the inverse of 2, 6, 6, 2, 7, 6, 2, 7, 7 inverse times B, 8, 10, and 9. 8, 10, and 9. So it will be 1, 2, and negative 1. Notice that the matrix X itself is XYZ. So two matrices are equal where the corresponding element, corresponding entries are equal. So X equal to 1, Y equal to 2, and Z equal to negative 1. Right. So in this section we learned about inverse of the matrix. For 2 by 2 matrices, we can find the inverse using this formula, provided that 1 over AD minus BC, the denominator here, is not equal to 0. If it is equal to 0, the matrix has no inverse. Once we know the inverse, we can use that to solve the system of equation. So system of equation, we just in the matrix form, A times X equal to B, so the solution would be X equal to A inverse times B. And so that's what we have. And that's all I want to cover in this section. Thank you for watching, and see you in another video in course algebra.